Hi everyone, my name is Lon. Before we launch into it, a big thank you and welcome back to those who have already subscribed. If you are new to the channel, please subscribe to be notified of future content, which will be coming soon. Right, what is an array? An array can be defined as a container object that holds a fixed number of elements of a single data type. Let's look at an example of an array. The first type of array we'll look at is a one-dimensional array. Depending on the requirement, you can also create multi-dimensional arrays and jagged arrays. The requirement for this example deems the use of a one-dimensional array to be appropriate. In this example, we want to store in memory final yearly grades for a particular student in sequential chronological order. So each value in the array will be an integer value that represents a final grade for each year that the student studied. We'll then write each of the values stored in the array to the console screen. We'll traverse each item in the array using a for loop. We'll look at examples of multi-dimensional arrays once we have discussed one-dimensional arrays. We'll then look at an example of a jagged array. So let's continue with our one-dimensional array example. Let's create a static method and we'll name it one-dimensional array. We'll make this method static because we are going to call this method directly from the static main method. If the method was not static, we would need to instantiate an object and then call the method on the appropriate instantiated object. The static keyword means the method is a member of the class in which it resides and not a member of the object derived from the class in which it resides. The static keyword will be discussed in more detail in an upcoming tutorial. So let's define our one-dimensional array. So each grade in this array will be represented as an integer. So we define the integer array using the int keyword. We then follow the int keyword with empty square brackets. Let's give the array a descriptive name. We'll call the array grades. So we follow the name by the equals assignment operator, then the new keyword, followed by the type of elements that we want to store in this array, which is denoted by the int keyword. Now here we need to indicate the length of our array. An array must be defined with a fixed length. You can see that we have not yet specified the length for the array, so the C# compiler is flagging this and underlining the offending code with red squiggly lines. So if we hover our mouse over the red squiggly lines, you can see the error message stating, array creation must have array size or array initializer. So you can initialize the array with values at the same time as defining the array, like this. In effect, by adding values at the same time as defining the array, we have also specified a fixed size of 4 elements for this array. So what happens if we defined an empty array and then tried to add values to the array like this? This results in a runtime error. The error message states, index was outside the bounds of the array. So when defining an array, you must specify the size of the array either with an explicit value denoting the size of the array or by adding a number of elements to the array at the same time that the array is defined. You can do this by either assigning values within curly brackets and using a comma to delimit the individual elements added to the array, or by including a value representing the size of the array within the square brackets as shown in the example, where we have explicitly included the number 4 within the appropriate square brackets to provision for the storage of 4 elements in this array. So in this example, we are declaring that we wish to store 4 values of type integer in a one-dimensional array named grades. And you can see how each value in the array could represent a final yearly grade for a student. Each index, which starts at 0, can denote a chronological sequence. Year 1 is represented by the index with a value of 0, Year 2 is represented by the index with a value of 1, and so on. Let's create the code that will write the values in our grades array to the console screen. We'll use a for loop to traverse the integer values stored in the array. This is important to note. We are using 0 as the starting index in the array. This means that the highest index of the array will always be 1 less than the number of elements stored in the array. So in this example, the number of elements stored in the array is 4, and the highest index for this array will be 3. Let's call the one-dimensional array method from the main method and run the code. Great! But we could have written this code better. Let me explain why. You can see that the code to define and populate the grades array is tightly coupled with the code that writes the values stored in the grades array to the console screen. If we want to define a greater size for our array and appropriately add more values, we also need to update the code that writes the values stored in the grades array to the console screen. This is why we can refer to the code that defines and populates the grades array and the code that writes the values stored in the grades array to the console screen as tightly coupled. If we change the size of the array and appropriately add more elements to the array, this change would not propagate through to the code that writes the values of the array to the console screen. So as discussed, we can resolve this issue by decoupling the code that defines and populates the one-dimensional array from the code that writes the values stored in the one-dimensional array to the console screen. So to do this, let's create a new method and name it WriteOneDimensionalArray to screen. This method will accept one parameter, which can be any one-dimensional array of type integer. Let's then cut the code that outputs the values stored in the one-dimensional array and paste it into our new method. Now we need to refactor this code to make it generic. What this essentially means is that the code will no longer be specific to a particular one-dimensional array. This code can be reused to sequentially write the values stored in any one-dimensional array of any size to the console screen. So to ensure that a one-dimensional array of type integer of any size can be appropriately handled, we can use the length property on the array object to return the length of the array passed to this method. All arrays are derived from the array abstract class. The array abstract class contains a length property that returns the size of the array. We need to subtract 1 from the value stored in the property because, as discussed, the greatest index value of the array will be 1 less than the number of elements stored in the array. This is because the first index of the array will be 0. If the code attempts to retrieve a value from the array that is 1 greater than the greatest index of the array, this will result in an index out of range runtime error. Okay, so let's call this method from within the one-dimensional array method. Now we can test whether we have successfully decoupled the functionality of defining and populating the values in the array from writing the values of the array to the screen by adding more items to the array. And you can see we did not have to alter the code that writes the values in the array to the console screen after adding more items to the array. The new items added to the array were automatically propagated through to the new method, WriteOneDimensionalArray to screen. Another important point to note about arrays in C# is that they are reference types. As discussed in previous tutorials, a reference type stores a pointer to where the actual data for the reference type is stored, which is a memory location called the heap. This means that when the array is passed from one method to another as a parameter, the same data is referenced in memory. So if the array is changed in the first method, the array data in the second method that references the same array data will also reflect this change. So this is a basic example of code reuse. Code to sequentially write all elements in a one-dimensional array of type integer to the console screen only needs to be written once. This code can be passed any one-dimensional array of type integer as a parameter, and it will perform the generic function of writing all the values of the elements stored in the array to the console screen in sequential order. So let's move on to multidimensional arrays. Let's first look at a two-dimensional array example. Let's create a method named toDimensionalArray, and let's define the two-dimensional array. The first thing we write when defining the integer two-dimensional array is the int keyword followed by open square brackets with a comma within the brackets. This indicates that we wish to define a two-dimensional array. So let's name this array Student Average Grades per Year. In this example, we are going to add the average yearly final grades for 3 students for each of the 4 years studied by the students. So the first dimension in the array denotes the number of years studied. These students have studied for 4 years. The second dimension represents individual students. This example is dealing with 3 students. So we are going to add a total of 4 multiplied by 3 elements to this array. We are then going to write the values of the elements in the array to the console screen. The data will be represented as a matrix. Each row represents a year studied. Each column represents a student. So let's populate all 12 values of the array. These are arbitrary values created for the purpose of this example. Let's speed up the process of populating the 2-dimensional integer array to save time. As always, the code created for this tutorial can be downloaded from GitHub. Details of the location of where you can find the code for this tutorial is under the GitHub code section below in the description. Okay, let's create a method to sequentially output the values of any 2-dimensional array that stores integer values to the console screen as a matrix. We have an outer and an inner loop in this method. The outer loop traverses the first dimension of the array. The inner nested loop traverses the second dimension of the array. So basically the code reads as, for each of the 4 years studied, output the yearly average grade for 3 specific students. Please note that we are using the getLength method, which belongs to the array abstract class, to retrieve the number of elements stored in the appropriate dimensions for our array. Remember, all arrays in C# inherit from the array abstract class. An integer parameter gets passed into the getLength method. The value of 0 that is passed into the getLength method for the Boolean expression in the outer loop denotes the first dimension, and a value of 1 that is passed into the getLength method for the Boolean expression in the inner loop denotes the second dimension. So in this example, the outer loop will loop 4 times, and the inner loop will loop 3 times for each of the outer loop iterations. Within the inner loop, code to write the array values to the console screen is implemented. Each array element is indexed appropriately, i.e. the outer loop x counter variable indexes the first dimension, and the inner nested loop's y counter variable indexes the second dimension of the 2-dimensional integer array. Let's run the code. And as you can see, we have a matrix represented on the console screen. The rows represent the years studied, the columns represent the students. So you can see student 1 scored an average grade of 54% in the student's first year of study. Student 3 scored an average grade of 82% in the student's 4th year or final year of study. Student 2 scored an average grade of 67% in the student's 2nd year of study. Okay, let's look at an example of a 3-dimensional array. So this example is similar to the 2-dimensional array example. We are going to store and display average yearly grades of 3 students, but the difference is we are going to split the data up into another dimension. So in this example, the 3rd dimension relates to the students. The 2nd dimension relates to the years studied. And the 1st dimension relates to the courses studied. So let's define our array. This time, the int keyword will be followed by square brackets containing 2 commas. This indicates that we are defining a 3-dimensional array. Let's call this array student average grades per year per course. Now let's define the size of each dimension. Remember, we have to fix the length for an array at the point at which the array is defined. So the first dimension will have a length of 2, denoting 2 courses that the student studied. The second dimension will have a length of 4, denoting the number of years the student spent studying, and the length of the third dimension will be 3, denoting the number of students included in this example. 2 multiplied by 4 multiplied by 3, so this array will contain 24 elements. Right, let's populate the data for this array. And let's fast forward through this rather laborious process. Okay, we have now written the code to populate the data for the array. Let's write the code to sequentially write the values stored in any 3-dimensional integer array to the console screen. So this code is very similar to the code writing the 2-dimensional integer array to the console screen. The main difference being that we have added another outer loop. And we of course need to include an index for our third dimension when writing the values of our array to the console screen. In the interests of better formatting, I've included a dashed line to divide the results of the first course from the results of the second course. Right, let's run the code. So what you have here is three-dimensional data represented on a two-dimensional screen. The first matrix represents data for the first course that the student studied. The second matrix represents data for the second course that the student studied. Let's look at some of the results. So, student 3 scored a result of 88% in the student's final year, i.e. year 4, of course 1. The same student scored a result of 85% in the student's final year, i.e. year 4, of course 2. Student 2 scored 67% for the student's second year for course 1. Student 1 scored 64% for the student's third year for course 2. Right, let's move on to jagged arrays. So in this example, we want to store and write to the screen the data of 3 students who enrolled for a 4-year course. You'd think that we could simply store the data in a typical 2-dimensional array, where the first dimension has a size of 4 representing the 4 years, and the second dimension has a size of 3 representing the 3 students. But now what if, for example, student 3 dropped out of the course after 1 year of study? As part of the requirement, we want to include this particular student's results in the array, along with the results of the other 2 students. If we used a typical 2-dimensional array, we would be allocating memory space for 3 items of data that we know is not needed. This is because for this student, only 1 item of data exists, i.e. the student's 1 year of study. There are no results pertaining to student 3 for year 2, 3, and 4. Let's also add that student 2 dropped out of the course after 3 years, but again we still want to represent the data for the 3 years that student 2 studied, along with the data pertaining to student 1 and student 3. So student 1 completed all 4 years of the course, and we would like to include student 1's results in the array. If we were to use a typical 2-dimensional array to store the relevant data for the 3 students, 4 spaces would be redundant, because we know we will never have data to populate these spaces. This is because 2 of the students did not complete all 4 years of the course. So the solution to avoid making provisions for redundant data can be to use a jagged array to store the data. This is unlike the definition for a typical 2-dimensional array, where the dimensions are delimited by a comma within one set of opening and closing square brackets. So, for the first year, all 3 students completed the year, so we have 3 elements of data. We can do this by including the data elements within curly brackets. The elements within the curly brackets are delimited by commas. So you can already see how we can achieve creating a jagged array. We are effectively adding an array of 3 elements to the first indexed item of another array. A jagged array is an array of arrays. Now, for the second year, 2 of the students completed the year, so we make provision accordingly for 2 elements of data. And it is the same for the third year. We have 2 data elements. The fourth year, remember student 2 and student 3 did not complete this year. We only have 1 element of data for this year pertaining to student 1. And you can already see the jagged pattern of the data in this array. So let's write generic code in order to sequentially write a jagged array to the console screen. Note that the Boolean expression for the inner for loop references each of the varying dimension lengths. Note the index for the first dimension of the array, representing the study year, is represented in the loop by the x counter variable. With this jagged array, space has not been provisioned for redundant data, as would have been the case if we chose to use a typical 2-dimensional array for this purpose. For the requirements in this example, a jagged array is the optimal solution to store and traverse the data. So for these tutorials, I like to introduce new concepts that are beyond the scope of the main focus of the tutorial. So for this example, we'll use an abstract class, an enum data type, and we'll also look at an example of using inheritance to implement code for the abstract class. We are not going to look at these concepts in great detail in this tutorial, but I'll provide an insight into how we can store custom objects within arrays and generically call their properties and methods while traversing them within a for each loop. So in this example, we are going to store 5 objects representing real-world objects in an array and write data pertaining to these objects to the console screen. We'll use a for each loop to traverse the objects stored in the array. So the objects we are going to store in the array are as follows: a London taxi cab, a 4x4, a speedboat, a Cessna aircraft, and a helicopter. So what do all of these real-world objects have in common? Yes, they are all people carrying vehicles. So this means we can abstract certain common functionality for these vehicles. So we are going to use an abstract class for this purpose. Let's create an abstract class and name it vehicle. An abstract class is like an interface in that it can contain, for example, method signatures or definitions that do not contain any concrete implementations. So an abstract class can contain, for example, methods and properties that are merely design elements. Unlike an interface, abstract classes can also contain, for example, methods and properties that do contain code implementations. Like an interface, an abstract class can also be used as a type when defining a variable. And also like an interface, an abstract class cannot be directly instantiated. The abstract class must be inherited by another class, i.e. it must be a base class for another class in order for it to be consumed in code. For our vehicle abstract class, let's first define a private member variable named numPeopleCanCarry. We'll initialize this variable to a value of 4. Let's also create a private member string variable named description. We'll give this variable the following default text: people carrying vehicle. Now let's create an enum. An enum allows the developer to enumerate a group of named integer constants. The first type of vehicle will be land, the second type of vehicle will be water, and the third type of vehicle will be air. Okay, so now using the abstract keyword, let's define a read-only property. The abstract keyword in this context forces the class that inherits from this abstract class to implement this read-only property. If the derived class does not implement this property, a compile time error will be flagged. We'll create an abstract method that returns the vehicle type enum. This means that any class inheriting from this abstract class must implement this abstract method. We will now use the virtual keyword while defining a method responsible for retrieving a description for the vehicle. The virtual keyword means that the code for this method can be overridden in the class that inherits from the abstract class. So this method will contain basic code implementation that returns the default text stored in the description private member variable. Then we will create another virtual method that returns the numPeopleCanCarry integer variable value. This variable denotes how many people the vehicle is able to carry. So now that we have completed our abstract class, let's implement it for the first object, the London taxi cab. So let's call this class London taxi cab, and we can use the colon followed by the name of our abstract class, i.e. vehicle, to indicate that we wish our London taxi cab class to inherit from the vehicle abstract class. And now you will see red squiggly lines under the London taxi cab text. So a quick way to get rid of the red squiggly lines is to click where it says Show Potential Fixes and then click Implement Abstract Class. And you'll see Visual Studio creates default implementations for the relevant abstract method and property, and the red squiggly lines disappear. So you can see that the override keyword is present for the method and property. This allows the developer to customize code for the methods and properties derived from the abstract base class. So here we are returning the appropriate custom name for this vehicle. We are also returning the appropriate type of vehicle. In this example, we are very basically distinguishing between land, air, and water for the type of vehicle. A London taxi cab was obviously a land vehicle. Note that we have not created custom code for the two virtual methods in the vehicle abstract base class that contains the virtual keyword. Unlike when the abstract keyword is used, you do not have to implement code for virtual methods or properties. You may decide that the code already implemented for the virtual methods or properties in the abstract class meets the requirement. But for this particular requirement, we are going to override these virtual methods. First, let's override the getDescription method. In this override method, we are going to return the default text returned by the abstract base class. To do this, we use the base keyword to reference the abstract class and call this override method's base counterpart method getDescription. Then we concatenate the custom text appropriate for this particular vehicle's description to the text returned by the base class's counterpart getDescription method on a new line. Okay, let's then override the vehicle abstract base class's method getNumPeopleCanCarry. We don't want to return the default value returned by the base class's counterpart getNumPeopleCanCarry method. So we'll replace the code base.getNumPeopleCanCarry with a value that is more appropriate to a London taxi cab. We are saying the London taxi cab can carry 7 people. This number includes the driver and the front seat passenger. I'm really not sure if it is accurate. Please let me know below in the comments section if 7 is the correct number representing the maximum number of adults that a London taxi cab can carry. So I'm going to fast forward the implementation for the other 4 derived vehicle classes for this example because the concepts associated with the abstract class are not the focus of this tutorial. Please feel free to download the code for these examples from GitHub so that you can take a more in-depth look at the code. Let's implement code for the 4x4 class, then the speedboat class, then the Cessna class, and lastly, the helicopter class. Right, let's create a method named WriteVehicleDataToTheScreen. Let's define an array that will contain our 5 vehicle objects and add newly instantiated vehicle objects to our array. Let's write the code to traverse the objects in the array. We are using a for each loop for this. And the code reads as for each vehicle in the vehicles array, output data relating to each vehicle. Okay, let's insert calling code for this method in our main method. And run the code. And you can see appropriate customized data for each vehicle, i.e. London taxi cab, 4x4, speedboat, Cessna aircraft, and helicopter is written to the console screen. As discussed in the previous tutorial on C# loops, the for each loop does not contain a counter variable and a termination Boolean expression, because a lot of the heavy lifting, as it were, is done behind the scenes. All arrays in C# inherit from the array abstract class. The array abstract class implements an interface named IEnumerable, which enables a lot of the implementation detail regarding the for each loop functionality to be abstracted. Please find the details of where you can download the code examples demonstrated in this tutorial below in the description. These details can be found under the GitHub code section. If you feel you have gained value from viewing this tutorial, please consider giving it a thumbs up. It will be greatly appreciated. And please subscribe to support the channel. If you're already subscribed, please smash the bell icon to be notified of future content, which will be coming soon. Please feel free to engage with me in the comments section. Thank you.